All right. So yeah, I just want to cover a couple examples for finding stable vectors, just so you guys have some more worked out examples to see as you're working on the activities and all that. So just once again, what is a stable vector? It's a vector W, a probability vector W, so that when I multiply it by the transition matrix, I get the vector back. I just get W back. So W is the stable vector. This is the transition matrix for the Markov chain, and it satisfies this equation here. And again, this only works for a regular Markov chain. So if it's not regular, I can't say that such a thing exists, that I can find a stable vector at all. I'm only guaranteed to have a stable vector if the Markov chain is regular. Let's see some examples of finding the stable Markov chain, kind of like we did yesterday. See a couple more of these. So let me suppose we have a Markov chain with the following transition matrix. So often we're just given the transition matrix right away, right off the bat. Need not always be the case, but we've talked before about how to find the transition matrix. And so I'll leave it up to you if you need to. So suppose we have this Markov chain represented by this transition matrix. We note that it's definitely a regular Markov chain because all the entries are already positive. So I don't have to worry about taking powers even. All the entries are already positive, so I know this is regular. So now I know it has a stable vector, so how do I find it? And again, just like yesterday, I had set up this equation here. From that equation, WP equals W, we have this. W times P minus the identity matrix equals 0. So we know this is true. And from here, what we did yesterday was basically write this out using variables for W. We write this out and simplify, and we get ourselves a system of equations. And then we go on and solve that system of equations, and that'll tell us what the entries of W need to be. So that's exactly what we'll do here. So basically W times P minus I. For W, I'm just going to write W1 and W2. These are just going to be placeholder variables for the entries of W. Our goal is to find out what they should be, what numbers those should be. And then P minus I is just take our P matrix and subtract the identity matrix from it, so the 2x2 identity. And what do I get when I do that? 1/4. So the 2x2 identity is this. So I'm going to subtract those. So 1/4 minus 1 is minus 3/4. 3/4 minus 0 is 3/4. 1/8 minus 0 is 1/8. And 7/8 minus 1 is minus 1/8. So here is P minus I, and here's W. So now I'm just going to multiply these out and see what I get. And I'm going to make sure that I keep in mind that this has to be set equal to 0, 0. Okay. That's what this, so basically I've just translated this equation into this line here. This is equal to 0. Okay. So since we have that, let's write down the corresponding system of equations we get by simplifying this out. And I'll note that in our system of equations, before I translate this, we always have to make sure that we include this equation, where the sum of the things in W equals 1, because I have to insist that W is a probability vector, meaning that its entries have to add up to 1. So I go ahead and I just include this equation always. I'll just do it first. And now I'm going to look at the equations that I get from this and add them to my system here. So I take this row vector times the columns of this matrix. So I'm going to get minus 3/4 W1 plus 1/8 W2. And then technically I should get another equation by multiplying this row vector with this column. But I think I told you guys yesterday that actually I don't need all of the equations that come from this down here. One of them will always be redundant. I basically have more than I need. It's easy to see in this case that that's true because if I look at what I get with the second column, I get 3/4 W1 minus 1/8 W2. I just get minus, oh, this should be equal to 0. I just get the negative version of this. And so they just differ by multiplying by -1. So clearly they're not really telling me anything different. They're basically the same equation. But in general, the reason this is true is just because if I include this last equation from this multiplying this row and this column, I'm going to have a third equation which means I'll have 3 equations, but only 2 variables. So like if I were to write out the augmented matrix, I would have 3 rows, but like 2 columns in my coefficient matrix. So I have more rows than columns, meaning that as I reduce this, I'm going to get a row that's just all zeros, which doesn't tell me anything interesting. So it tells me that I could have gotten rid of one of the rows in the first place, so I could have gotten rid of one of the equations. So I can stop here. You basically don't ever have to multiply with the last column if you don't want to. You can save yourself some work and just look at everything except the last column. Okay, so that is my system of equations that I now need to solve. Taking this equation and taking one of these that I get from multiplying this row and say the first column and setting it equal to 0. So now that I have that, we just solve this system. And we know how to solve systems. I'll run through this anyway, just because I'm going to go ahead and do it with matrix methods, because it's good to be practiced on those. So I'm going to convert this to an augmented matrix. So it's going to be 1, 1, 1, and then negative 3/4, 1/8, and then 0. And so now my goal is to reduce this augmented matrix. So what do I want? I want a 0 where that 3/4 is first. I already have a 1 here. I want a 0 here now. So I'm going to take 3/4 times the first row. I'm going to add it to the second row. And what will happen? I'll get 0. What's 3/4 plus 1/8? I think it's 7/8. You guys might want to check that. I think that's 7/8 though. And then I'll get 3/4 times 1 plus 0, which is also 3/4. 1, 1, 1. Okay. Now, the first column looks good. I need to get a 1 where the 7/8 is. So I'm going to like divide the second row by 7/8, or if you like, I'm going to multiply it by 8/7. It's the same thing. So I'm just going to divide this all by 7/8, which is the same as multiplying it by 8/7. So I'm definitely going to get a 1 here, because 7/8 divided by 7/8 is 1. What's 3/4 times 8/7? I believe we're going to get, what, 6/7? 6/7 if I carry that out. And then I have 1, 1, 1. Okay, and so we're almost there. I just need a 0 there quick, and then we're done. And so how do I get that? Well, I already have 1 and 1, so I'm just going to take -1 the second row and add it to the top row. So basically it's going to take row 1 minus row 2, if you will. And what happens? Well, we get 1, we get 0, and then what's 1 minus 6/7? Well, it's 1/7. And I'm done. Okay. So this tells me then that W is 1/7 and 6/7. These both add up to 1, so that's good. It looks like we're probably correct. And in fact, if we keep that in mind, I might point out that actually I could have skipped this last step here, because I've already found one of the answers, 6/7. And I know that the 2 values have to add up to 1. So I can basically just take 1 minus 6/7 and I'm done. I don't need to add this whole row or whatever to the other row. I could kind of just, from here, figure out, oh, the other one had to be 1/7, because what I need something that adds to 6/7 to give me 1. That's 1/7. So in some sense, I could have like stopped here and figured out that it's 1/7. But we could also just finish the matrix procedure, and that's fine too. So as you get more comfortable with these, you might notice little shortcuts like that. I'll point them out as we go occasionally, but you can always, if you don't feel comfortable taking a shortcut like that, just take it all the way to the end. There's no harm in that either. So, but like if you were on the exam and you were submitting your written work, and you just kind of stopped here and you said, since I know this one is 6/7, the other one's 1/7, I'm totally cool with that too. That's fine. So, I encourage you to make leaps like that, to take little shortcuts, as long as they're justified. And in this case, we are definitely justified. So I encourage it. So anyway, here is the completion of this example. We found this vector. So I might just point out, if you want to check your work, again, to check your work, if you're ever just concerned whether or not you got the correct answer, there's maybe 2 things to check. One is that the W's add up to 1. right? So you might want to check that this is true. And of course, in our case, it is. The other thing that you might want to check is the fact that WP actually equals W. You might go ahead and just do this multiplication, W times P, to make sure that you really just get W. If you try to do this and you get something else, then you've made a mistake somewhere and you need to go back and check your work. So these are good quick checks to do just to make sure that you did everything right. So I just wanted to point that out. So it's good to be in the habit of checking your own work, being able to sort of grade yourself so that you can fix any mistakes that you might find. But okay, so I'll pause and ask if there are any questions about this example or just about any of the stable vector stuff in general. Okay, so it doesn't sound like it. So I'm going to move on to another example. Basically the same kind of style here. But more complicated.